What is the title of this chapter? Sophie. Rationals.
Patterns in addition and subtraction.
All right, today we're going to start our conversation really on rational numbers. So we're on page 224. Yeah, I'll grab that in a little bit. How about that, John? Thank you very much. So we're talking about rational numbers. Now, I hope you guys are aware that there's not just one type of number out there. In fact, we're going to talk today about 3 types of numbers, and there are more. I'll kind of allude to another one. So we're talking, first of all, about rational numbers. But before I get to rational numbers, I'll use this one. No, this is not a good color. I'll go with sets of numbers. Let's talk about the sets of numbers that we already know. So this is our first part of this lesson. And this is important because you need to know this for your homework. And the definitions that I give are going to be based on these types of numbers, these sets of numbers. So the first set we're going to talk about whole numbers. Does anyone know what whole numbers are? Michael.
Counting numbers in zero.
Whoa, very nice. That's actually exactly it. I'll put the counting numbers, and 0. Okay, the counting numbers and 0. So when I count naturally, I count 1, 2, 3, 4, 5, 6, 7, 8. And I think I've probably said this, but when I'm teaching my son how to count Ezra, because he's getting to that age, I'm like, all right, Ezra, 1, 2, 3. What was cool is a few months back, we're driving down. He loves cars, and we're driving down the road, and it was near downtown, so a lot of parked cars on the side. And all of a sudden, randomly, out of nowhere, he starts saying 1, 2, 3. As we're passing by, I'm like, are you kidding me? And he was counting a little bit. Now, when he started counting, did he count like this? 0, 1, 2. Now, how did he start counting? He started at 1. So 1, 2, 3, 4, 5. Those are called natural numbers or counting numbers. We're going to start off, though, with the whole numbers. And that's all the counting numbers, 1, 2, 3, 4, 5, 6, 7, and the number 0. So those are whole numbers. Number 2, the second set, we're going to call those integers. Integers. And we've dealt with integers already. Does anyone know how to classify or define integers? John?
The counting numbers and their opposites.
Super close. Oh, you're so close. You had it. There's one little word I would replace. Max?
A whole number and its opposite.
Whole numbers and their opposites. Very good. And I'm guessing you thought that, John. But it'd be the whole numbers and their opposites. The whole numbers and their opposites. So, in order to understand integers, don't you need to understand what whole numbers are? Because if you're like, what's a whole number? Do you really know what an integer is? Not super. So, the whole numbers and their opposites. All right, whole numbers. 0, 1, 2, 3, 4, 5. What are the opposites? Negative 1, negative 2, negative 3, negative 4, so on and so forth. Those are all classified as integers, okay? So negative 555 and positive 412, they're all integers in between there when you're thinking about whole numbers and their opposites. And then today, the third category, which we're going to spend the most time with, rational numbers. When you think rational numbers, what do you think is the opposite of rational? What do you think? Irrational, right? That was a rational thought, or that was a rational argument. That was irrational. That is an irrational argument, okay? There is somewhat of that idea, rational, irrational, but actually the key I want you to get is this. In the word rational, there's a word ratio. That's a key component to rational numbers. And this definition is a little bit more involved, okay? So go ahead and write this down as I read it. Any number that can be I'll scroll up here. Any number that can be expressed. That's a nice word for numbers. In the form A over B. So that's the form. And there's a little bit with that form that you need to know. So in the form A over B, where A and B are integers and B cannot equal 0. It is a huge definition. Super important though. And it looks long, but you'll see it's actually not too bad. So any number that can be written in the form A over B, where A and B are both
Integers.
and where B cannot equal
0.
All right. Man, this is a picky definition. Doesn't it seem like not a lot of numbers would fit this definition? Like it's really restrictive? It's actually not. It actually has more numbers than either of the two categories. I don't want to say combined, but either one of those categories separate. All right, ready? A rational number. Let me give you a simple rational number. I'm going to go here with 19. That's a rational number. And you're like, wait, how can that be rational? All right, ready, guys? Let's look back at our definition. Can this number be expressed as a fraction of integers? Yeah, can it be written out as 19 over 1? Okay, are 19 and 1 integers?
Yes.
Is 1 equal to 0? Is that a rational number? Yes. All right? So, let me give you this little hint. All integers are rational. All whole numbers are rational numbers. So, let's draw a little diagram. Nope, 0 can also be. I'll show you how 0 works. Okay, have you guys heard of Venn diagrams? I think it's in your book, a Venn diagram. Basically, they're like little circles or ovals or little diagrams to help you show how things relate to one another. Okay, I want you to draw kind of a smaller circle, and I want you to write in there whole. All the whole numbers can fit in that little circle there. All right? And then we had the integers. Well, the integers is a bigger circle that has all of the whole numbers as well. So let me ask you this question. Based on this diagram so far, is a whole number also an integer? Yes. A whole number, like 0, is 0 also an integer? Any whole number is also an integer. And then I want you to draw an even bigger circle around those two circles. And what do you think I'm going to write in that one? Rational. Rational. Or rational numbers I could put. All right, ready, guys? Let's talk about logic. How many of you think you like logic? You like it. How many of you think I don't think logic's that cool? Honestly, yeah, I'm okay. I'm okay with either one. All right, fine. Ready, guys? Listen up. Everyone listening up. I might call on individuals. All right. Are whole numbers, don't say that loud, I'll call on people. Are whole numbers integers? Caroline. She says yes. Whole numbers are integers. Very good. Are integers rational numbers? Mackenzie.
Yes.
Yes. Okay, wow. You guys are too good at this. Braden. Are all integers whole numbers?
No.
Wait, are all integers whole numbers?
Yeah.
Yes.
Which one, yes or no?
Yes. No.
You had it right the first time. You had it right, yeah. All the integers are not whole numbers, but are all whole numbers integers? You see how that's logically, one can be, this group fits into this big group. But does this big group fit into that small group?
No.
No, and you can see by the diagram, I hope. Okay, ready, Max?
Oh no.
All rational numbers are whole numbers.
Yes. Because logic.
Because logic. All right, let me ask. I'm going to phone a friend for you. Sophie, all rational numbers are whole numbers.
No.
All the rational numbers are part of the whole numbers.
It's like one of those baby.
Which one is it, yes or no?
Yes. False.
Wow, this is interesting. All right, Josie, I'll give you a chance. All the rational numbers are whole numbers.
Oh, no.
Really? Okay, the way you can really think that through is like, I kind of get the picture, but let's think of it like this. I'm going to give you some examples of rational numbers that are not whole numbers. Okay? So let me give you a rational number. Ready? Another rational number would be 1/2. Okay. Can this be expressed as a fraction of integers? Well, it already is. So is 1 and 2, are they integers?
Yes.
Is this number 0?
No.
This is a rational number. Now, is this number a rational number? Yes, I hope you're just listening to me. Is this number a whole number?
No.
No. So I have one example of a rational number that is not a whole number. All right, how about this? Is this a rational number?
No. Wait, yes.
Yes.
19 over 1.
Because it could be written as 19 over 1. Is this also a whole number?
Yes.
Yeah. So here's logic. Ready, guys? I'm going to see if you guys are thinking. Some rational numbers are whole numbers. True or false?
True.
True. All rational numbers are whole numbers. True or false? False. You guys get that? The words all and some mean a whole bunch. Okay, let's keep going here. Basically, with rational numbers, you're thinking of integers. So those are rational numbers. And then fractions. Almost every fraction, and I guess I could say really any fraction, or mixed number is also a rational number. And then I'm going to put here and decimals. And I'm going to put here, have you guys ever seen the asterisk after some word or phrase in a book or anything? What does that mean? Mackenzie?
It means like there's additional information about it.
Okay, so I said integers, fractions, and decimals, asterisk. So it says like see note below. Usually it's like this. 1 out of every 5 people will win, asterisk. Down there it says your probability of winning is not very high. So they're trying to give you more info. Yes, 1 in 5, but that doesn't mean that you will win if you try 5 times. So yes, when they put like an L or an A, they want you to look at the little note. This verse or this word means this. Or look at this passage. Yep, definitely how it works. All right, here we go. Let's look at decimals here. There are 2 types of decimals I want you to get. Decimals that are called terminating decimals. What do you think terminating decimals are? Raise your hand. Terminating decimals. Yes, Elizabeth?
They like simplify all the way.
They simplify all the way. Okay. I think I see what you're saying. Let's see if we can clarify that, though, because technically another type would also simplify all the way. Yep.
It's even out into a whole number.
I guess they could, but not necessarily. This is a tough one. Terminating decimals. Emma Grace?
Every terminating decimal can be written as a fraction of the denominator of 10, 100, or 1,000.
Oh, wow. You gave me a technical definition. You mean like example number 1? Okay, let's get an example of terminating decimals, and then I'll give you a definition at the end. All right. Can someone read example number 1, please? Marissa, on page 225, read example number 1.
Okay, the average adult's fingernails grow 0.125 inches each month. Write 0.125 as a fraction.
Really? Cool. Okay, anyway, sorry. We have to change that number into a fraction. Okay, 0.125. 0.125. This is an example of a terminating decimal, and all it means is this. Does this decimal continue on forever and ever and ever? Does it repeat or just keep going? Nope, it terminates. It terminates in what place value? By the way, anyone know? Thousandths place value. That's a terminating decimal. That's all it means. It ends. All right, how would I write this number as a fraction? Because this is part of what you're going to be doing. And I already gave you a hint. Yes, Callie?
Is it 125 over 1,000?
How in the world did you get that?
Because it ends in 1,000.
Wait. You're telling me that the way I read the decimal is the way I can write the fraction? Ready? Everyone read this with me. I'll read it once by myself. 125 thousandths. All right, ready, set, go. 125 thousandths. Isn't that the fraction? So, yes, a terminating decimal can have a denominator of 10, 100, 1,000, 10,000, any power of 0, by the way. But is this in simplified form? Yes, simplified all the way. Oh, my.
I know what the answer is, though.
Yes, the book gave me the answer. How did they get it?
They did some math stuff and divided it by 5 a lot.
I know it.
Okay, they use the GCF or they just divided by common factors. So would you?
GCF is 125?
Yeah, the GCF of 125 and 1,000 is 125. So how many times does 125 fit into 125? Once. How many times does 125 fit into 1,000? 8 times. All right, that's the way. If you knew the GCF. Sorry, I hear talking. But if I didn't know that, because maybe I didn't know the GCF was that, then just divide it by common factors. What goes into 125 and 1,000? 5 goes in it. Does 25 go into both?
Yes.
So you can divide both of these by 5, or you can divide them both by 25. The higher number you get, the easier this becomes. So I'm going to use 25. How many times does 25 go into 125? 5 times. The tougher part is how many times does 25 go into 1,000? 40. And then, is this simplified? No. So what do I divide both of these by?
5.
So 5 goes into 5 once, 5 goes into 40. So 1/8, whichever way you took would have gotten you there. Just be careful when you divide. Make sure you get a common factor. All right. How many of you think you know how to do this process? Changing a decimal into a fraction. Okay, if you don't, or if you do, I want you to practice on page 227. I want you to do numbers 7 and 8. So rewrite those as fractions in simplest form. 7 is 0.05. And if you don't know how to do it, I can help you out here if you're maybe confused.
To add the 0 if we need to.
You mean at the beginning? No. Okay. How would I read this number? How do I read this number? Jack? 5 hundredths. And that gives me a clue on how to write it. But is that simplified form? Is that as simple as it can be written? No. What goes into both of these? 5. 5 goes into 5 once. 5 goes into 100 20 times. So it's 1/20th. All right. Number 8 is a mixed number. So you need to be very careful with that. I think it's a negative. And it has 9.64. Negative 9.64. Oh my. How do I read that number? There is a way to read that, but yes.
9 and 64 hundredths.
Yeah, negative 9 and 64 hundredths. If that's it, then I simply have to reduce that fraction, 64 hundredths. What's the GCF of 64 and 100? There's another number. That is a common factor, but there's a greater common factor. 4. 4 goes into 64 16 times. And 4 goes into 100 25 times. That's my answer, right?
No.
Oh, wait, sorry, negative. negative 9 and 16/25. Don't change the sign of the number that they already gave you. I'm going to ask you guys a deep question. So once you're done writing that, I need to ask this deep question. So please pay attention. You thought logic was tough. This one's going to be tougher. All right. If you're looking up on the board, you know what I'm talking about. I'll scroll up for some of you. Okay. The problem on number 8 was change negative 9.64 into a fraction or mixed number. Okay. Is negative 9 and 16/25 equal to negative 9.64?
Yes.
Sure about that?
Yes, it is.
Okay, so this is what I want you to know. When we're changing this decimal up there, negative 9.64, into negative 9 and 16/25, we're not changing the value, we're changing the form. Okay? So we went from decimal to fraction. Now that was a tough question. Did you get it? Is that bad? No, okay, good. Because it'll get tougher as I keep going with this idea. Anyway, is this a rational number? Okay, I see mostly affirmative answers, but can this be written as a fraction of integers? Where A and B are both integers and B does not equal 0?
Yes, you can.
You sure about that?
I know she is.
Do it. Write it that way.
Okay.
It is not in that form. I just want you to write it. Oh, man. Try it real quick. Write it. That means you're using a pencil. I don't know. Wait, huh?
I'm confused.
So how do I change this mixed number into a fraction? Because right now it's a mixed number. That means it has a whole number part and a fraction part. How do I change it to a fraction? Do you guys remember this? Multiply and add. Do you guys remember how to change a mixed number into an improper fraction?
Yes.
That's what I'm asking.
Shush.
Wow. All right, how many of you, and this is something you have to know, not particularly for this lesson, but you should know it, how to change a mixed number into an improper fraction. So you multiply 25 times 9, what's that? 25 times 9. 225. Then you add the 16, you get 241. And then you just write 241 over 25.
Negative.
Yes, negative, right here. Is this number right here and this number right here integer? An integer. Yes. Is this number right here not equal to 0? Is this a rational number? Is this a rational number?
Yes.
Ooh. See, remember I told you if one number equals another? I asked you that. Okay, is that a rational number, everyone?
Yes.
Yes. Is that a rational number, everyone? There, yeah, I think you're thinking it too. And is this a rational number?
Yes.
Okay, because these three equal one another and one is a rational number, all three of them have to be rational numbers. That's logic. That's logic. If these three numbers are the same and one of them is a certain type of number, all of them are that type of number. Exactly. We're just changing the way it looks. It's like this. Tomorrow, I hope not to come in the same outfit. I don't know. Maybe I will, but surprise you a little bit. I'll come in a different outfit. As you come into the room tomorrow, you're going to notice he is not wearing the same thing. So now he is not Mr. A. He is Mr. A
In a new outfit.
to the second power.
He's Mr. B.
He's Mr. B. Yes. Does my identity change when my clothes change? No. Well, depends if I'm a superhero, and then yes, I do. Okay. Plastic surgery. Oh my. Okay, we're thinking too hard about that. The second type of rational number dealing with decimals is going to be repeating decimals. You guys remember repeating decimals? So one example of a repeating decimal would be 0.44444 dot dot dot. What does the dot 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 mean? Yes, ma'am? Keeps going on and on. So the way I write this number, the way I write this repeating decimal number is by simply using it's technically called a repeating bar or a repetend bar. This right here means this. Which one's easier to write? The one with the bar, right?
This one's fun.
The one on the left. The one on the right's a lot easier. So they mean the same thing, but repeating decimals are also rational numbers. This right here can be written as a fraction of integers. Now, if you're looking at example 2, if you turn the page at 226, if you're not there already, there is a process for making this number into a fraction. It is not easy, and I am not going to take the time today to go over it because we will go over it next year. Or should we go over it this year?
Can you just round it?
No, don't round it. If you round it, you technically change the value a little bit. If you round it. A little bit, yes. Okay, but we're going to say repeating decimals are rational numbers. Okay, if I had this number right here, 6.232323 dot dot dot. How would I write that as a repeating decimal with the repeating bar? You got to be super careful with this. Caroline. 2 and the 3. Okay, good. Good. You put the line over the digits that repeat in the decimal, on the decimal side here. Let me give you a way not to write it. This is the way I do not want you to write it. Okay, ready? Same number. 6.2323. Okay. Hopefully it's the same value, but we call it, I like this one, I've been using it for many years. We call it redundant. That means it's unnecessary. You should put that repetend bar the first time those digits come up if they're going to repeat. This is saying the same thing, but it's being redundant or unnecessary. So if you write it like this and you circle it, it's going to be marked wrong. This is the way you need to write it. There's a proper way to write it. Well, the squiggly line does not apply here because it means exactly that, or this means exactly that. The squiggly line is when you round. Or change it just a little bit. Yep.
Or if you write two little bar things instead of just one.
Like you put a space here.
No, you put like another one. Yeah, like that.
Thankfully, it still shows in the illustration. I got to mark it wrong. Thank you for asking.
What if you do it like the 6.23, but on the 2-3 part you put 2 little dashes instead of 1 dash? Like it goes like.
I don't think I heard most of what you said, Bella.
It's 6.23.
But I think I'm going to do this.
No, yeah. What about if you put 2 lines above the 2.3?
So I mean like something like this?
Yeah.
Mark it off. Yeah,
Does
that's the
that
proper
mean
way.
something?
The double line?
Yeah.
Not that I know, no.
It's a line.
And that might confuse people since it
So
doesn't.
when you say redundant, is that kind of like putting a 0 at the end of a decimal?
Yeah, that would be another redundancy. The extra zeros here, if this was not repeating, you don't put those in there, you take them out. Terminal zeros, we call those. Okay, let's look at example 3. This will be the way you're going to use that Venn diagram. So kind of going back to that, reviewing example number 3. So you're not doing problems like example number 2. Okay, you're not changing a repeating decimal into a fraction, although you could. It just takes, it unfortunately takes a long time to explain and to do. So example 3, name the set or sets of numbers to which each number belongs. So A, we start with the number -7. All right, you guys can write that down. I'm going to scroll all the way back to my Venn diagram to show you how I would do this problem. Okay, is -7, I start with the innermost circle. Is -7 a whole number?
Yeah.
No. Okay, so I move up. Is it an integer?
Yes.
Yes. If it's an integer, it also has to be a
Rational.
rational. So for my answer for giving the categories that -7 belongs to, I said it was an integer, I'll put I, and it also has to be rational, we'll say R. I and R. That would be my answer for A. B, -3 and 2/5. -3 and 2/5. All right, I look at my innermost circle. Is it a whole number?
No.
Is it an integer? No. Is it a rational?
Yes.
So it's a rational, and that's it. Basically, your choices are WIR or...
So if it's W, it has to be rational.
Exactly. If it's W, it has to be I and R as well. Very good. Yes, sir. Dot. Okay. Oh, actually, I think I had 3 5s right here, just so I don't confuse anyone. Dot.
Does it matter if you have more than 1 5? Yeah, it does.
Yes.
Never mind.
It will throw you off. Okay, ready, guys? Let's just go through the process. All right, is that a whole number?
No.
No, it doesn't belong in that innermost circle. Is it an integer?
No.
Now, the toughest question, is it a rational number? Well, first of all, it's a decimal. Does it terminate? No, it keeps going. So it's not a terminating decimal, but is it a repeating decimal?
Yes.
Not exactly. We say no. So you know what category this fits into? None of them. Whoa. This number is strange. That's a real number, by the way. But it is neither whole, integer, or rational.
So it's not irrational?
Remember this is the Venn diagram? This is where you have to be careful with your Venn diagram. Some of you are already thinking, okay, it is not rational. It's not integer. It's not a whole number. It is a separate category, part of the irrational numbers. It's outside rational, and it's not a part of them. So let me give you this with the Venn diagram. Ready? Can a number be rational, according to my diagram, can a number be rational and irrational at the same time? No. It's got to be one or the other. We call that mutually exclusive. And I've used that word before. Let me give you a reminder. Ready? And this goes contrary, unfortunately, to our culture, but not to genetics, science in general, and the Word of God. If you are a boy, you are not a girl. And if you are a girl, you are not a boy. And I have no problem saying that because not only through the Word of God does it say God created male and female, it's very clear, but also by science, in your genes it says you're male or female. It says it. In every cell in your body, and every DNA structure, it says you're male or female. That's all it says. So, if you're one, you can't be the other. They are mutually exclusive. You can't be both at the same time. You've got to be one or the other. Can you be a Warriors fan and a Cavs fan at the same time, Tristan?
No. That is
You can't do that. All right. So some of you are like, I don't care.
It's basketball.
How about this? Can you be a girls basketball player and a boys basketball player at the same time? Same time.
No.
Here at MRCA. Okay, good. So you got it. I got to clarify all that because a lot of you come up with these instances. All right. Is this number a whole number?
No.
Is it an integer?
No.
Is it a rational?
Yes.
Yes, it's a terminating decimal. It is rational. If it ends, it's rational.
Wait, I have a question.
Yes, sir.
If there's a number, how do I say this?
Sounds like
If there's a whole number, it's everything, right?
It's whole, integer, and rational. Yep. But if it's a whole number, can it be irrational? No. Yeah, irrational, rational are separate categories. You can't be both of them at the same time. Good.
What
Yes?
about if it's a decimal that's also a fraction? Like it's like 3 point whatever it is.
And a
over-
half.
Yeah.
Okay. That's still going to be considered a rational number. But that's good. So I think this. Let me just give you this. This technically does happen, especially in statistics and business. They give you this, so that would also be written as that. So that's rational. Oh, actually, gas prices. Remember? They're like
They have like
They're like this, and they say and 9/10. That's still a decimal or a fraction. Go look at a gas station. Look at the prices. You'll see a fraction 9/10.
It says like actually it just says like 0.9.
Or 0.9. I guess older ones would have it, but yeah, 0.9. Yep.
Wouldn't 0 or 0.045, or if it was like you wrote it out 0 or 1/2, and if you put it as 0,
0.45.
yeah, wouldn't that be? Oh, never mind. You put the point in the middle.
All right, last example here. I think this is going to be one of the toughest parts, so please listen up. Example 4 on the top of page 227. It says to use a number line to choose a greater number from each pair. You don't, and the homework will say you can use it if necessary, so you don't have to do it. I'm not going to use it until I really need it, but I want to see which number is greater, -2/3 or -1/2. This problem isn't too bad, but I think it can get tricky when you start getting different numbers. When I look at these two, I'm thinking, just take a guess, 50-50. What I can do is I can give common denominators, and then I can compare them very quickly. So what's the LCD of these two fractions? 6. Good. You guys get that. So I'm going to multiply this fraction by what number? Be super careful to make it have a denominator of 6. Yes?
In the form of 1.
-2 over 2. So I get -4/6 when I multiply this by 2 over 2, right? What do I multiply -1/2 by to have a denominator of 6? Jack?
3 over 3.
Good. 3 over 3, so I get -3/6. Now this is very clear which one's bigger and which one's smaller. Yes, sir?
Wait, isn't it a negative? If -4 is closer to -1, -3 is closer to 0, then what is -3?
Yeah, and this is where if you're looking at negatives, I might as well draw that little diagram. Wouldn't -3/6 go right here? -3/6 would go right in between these two. Oops, -1. And then -4/6 would go somewhere around here. So which one is bigger? Which one is greater? The problem. -3/6, which means -1/2. You got to circle the original number that they. Go ahead.
What about if they weren't decimals? Wouldn't 3/6 still be bigger?
Oh, this is if they weren't
Negative.
4/6 would be bigger. Yeah, 2/3 would be bigger. Because wouldn't 2/3 be like over here, and 1/2 would be right here.
Okay.
So you got to think of it with the negative signs. That is tricky. Okay, and then B is a little tricky, and I think again this is going to be the trickiest one because one number is a decimal and one number is a fraction. And by the way, these are very close together. They're very close in value. I would recommend you turn them both into decimals. Both into decimals. So do you have to do anything to this guy? Nope. But how do I turn a fraction into a decimal? Do you guys remember? There's a specific way to do it, and you can always do it this way. Okay? That's if you had like a division of another fraction. Ready, guys? Michael?
Couldn't you multiply by 10 and that would be the 30, then divide it by 30, and it would be like 1 over 10, and it would be like whatever it is.
I guess I kind of see what you're doing, but that could be a little bit tough. Ready? You just divide. You do 1 divided by 3. 1 divided by 3. And this is going to give you a clear indication. You're like, man, you got to do it. What's 3 into 10?
3.
And then that's 9. Bring down a 1 and a 0. 3 goes to... You know it's going to be 3 repeating. It's going to keep going that pattern. So which one's bigger, 0.3 or 0.3333333? 0.3333 is bigger because this one would be...
Just 0.3.
Or 0.330. Sorry, 0.30000. So we would say 1/3 is greater. 1/3 is greater. Slightly. Yep.
Okay, so for the 0.33, couldn't you just write it 0.3 with a little repeating sign over it?
Sorry, say that again.
Okay, instead of writing 0.33, couldn't you just write 0.33? You have to write 33.
Oh no, the reason I write 0.33 is because I can compare that with 0.30 right away. But if you know that this is bigger than that, it's okay. It's just one method of doing it. Yeah, so there's not just one way of doing it. You can do it multiple ways. I would say this: if you have a fraction and a decimal, change them both into decimals. It's going to be the easiest. If you try a fraction, it could be a little bit tougher. Because what would happen, this becomes 3 over 10, and that's still 1/3. What's bigger, 3 over 10 or 1/3? Now we know what it is, but not necessarily by just the fractions. Okay, your assignment is, and it's a little bit different today, it's 19 to 23 odd. Yeah, just wait for the whole thing. 19 to 23 odd, and then 31 to 49 odd. And that's going to be pages 227 to 228. You're welcome.